Developing carbon capturing, sequestering, renewable, and clean industries. To build industries that capture and sequester carbon while producing renewable and clean energy, materials, and products, we must transform existing industrial systems and develop entirely new production models that align with natural carbon cycles. This means shifting from fossil fuel-based industries to bio-based, circular, and regenerative processes that actively remove CO2 from the atmosphere while producing valuable goods. Carbon capturing and sequestering technologies in industry. A truly carbon-negative industry must not only reduce its emissions, but also actively remove CO2 from the air and store it in long-term sinks. Key carbon capture strategies. Bioenergy with carbon capture and storage, BCCS. Biomass, e.g., wood waste, algae, crop residues, is burned for energy, and the emitted CO2 is captured and stored underground or converted into bio-based materials. Example: BCCS power plants that generate electricity while locking away CO2. Direct air capture, DAC plus industrial utilization. Machines that pull CO2 directly from the air, using renewable energy. Captured CO2 can be turned into fuels, building materials, and industrial products. Example: CO2-based cement and synthetic fuels. Biochar production for soil sequestration. Organic waste is pyrolyzed, heated without oxygen, to produce biochar, a carbon-rich material that stores carbon when mixed into soils. Helps improve soil fertility and increase agricultural yields. Algae-based carbon capture and biomaterials. Algae absorbs CO2 at a much faster rate than trees and can be used to create biofuels, bioplastics, and even food supplements. Example: algae farms near industrial zones absorb emissions and convert CO2 into bio-based products. Ocean-based carbon sequestration. Kelp farming captures CO2 and can be processed into biofuels, biodegradable plastics, and animal feed. Ocean alkalinity enhancement helps remove CO2 while restoring marine ecosystems. Renewable and clean energy industries. Replacing fossil fuels with carbon-negative energy. Bioenergy and biomass power plants with carbon capture. Convert plant-based materials into electricity and heat while sequestering carbon. Example: wood waste, crop residues, and algae biofuels replacing coal and natural gas. Hydrogen from organic waste and biomass. Producing green hydrogen from organic materials instead of fossil fuels. Carbon negative when paired with carbon sequestration. Solar and wind energy expansion. Integrate solar panels with green infrastructure, e.g., solar-covered farms, solar highways. Develop offshore wind farms with integrated algae carbon sequestration. Geothermal and tidal energy integration. Utilize deep earth heat and ocean movements to produce reliable, renewable energy. Carbon-negative manufacturing and materials. Transforming industrial production. Carbon sequestering concrete and bioplastics. Traditional cement is responsible for 8% of global CO2 emissions. New materials made from algae, biochar, and CO2-infused concrete can lock away carbon permanently. Hemp, bamboo, and mycelium-based construction materials. Replace steel and concrete with high-carbon storing plant-based materials. Example: bamboo skyscrapers, hempcrete homes, and fungal-based insulation. Regenerative agro-industry for plant-based textiles and packaging. Replace synthetic textiles with carbon-storing fibers like hemp, algae, and bamboo. Develop biodegradable, plastic-free packaging made from mushrooms and seaweed. Carbon-negative metals and mining innovations. Use biological processes, bacteria and fungi, to extract minerals instead of high-emission mining. Example: bioleaching bacteria that extract metals while absorbing CO2. Circular economy and zero-waste industrial models. Turning waste into carbon capture opportunities. Industrial symbiosis, closed-loop systems. Industries share waste streams. One company's waste becomes another's raw material. Example: captured CO2 from steel plants is used to grow algae for biofuels. Waste to biochar and biofuel systems. Convert agricultural and industrial waste into biochar, biofuels, and fertilizers. Captures and locks CO2 into the soil. Regenerative water and nutrient recycling. Use constructed wetlands and algae farms to purify industrial wastewater while capturing CO2. Example: algae-based wastewater treatment plants that also produce biofuels. Decentralized and localized manufacturing. Microfactories and distributed production. Localized, on-demand production. Reduce shipping emissions by using 3D printing and digital fabrication hubs in local communities. Use biodegradable and plant-based materials in localized production. Community-run renewable energy grids. Develop microgrids powered by solar, wind, and bioenergy to decentralize energy supply. Example, villages that produce their own energy from waste-to-energy systems. Scaling up carbon sequestering industries globally. To make these industries mainstream, governments, businesses, and communities must collaborate to scale production and implementation. Policy and economic incentives. Carbon pricing and tax benefits. Industries that capture more CO2 than they emit get tax incentives and subsidies. Polluting industries pay carbon taxes that fund carbon-negative projects. Public-private partnerships, PPP, for green industries. Governments invest in R&D for carbon-negative technologies. Private companies receive funding for transitioning to net-negative production models. Investment in innovation. Funding carbon-negative startups. Develop venture funds specifically for bio-based industries, carbon capture startups, and regenerative manufacturing. Example, direct investment into companies making biochar, carbon-negative concrete, and algae-based products. International carbon markets and trade. Establish a global carbon marketplace where industries buy and sell carbon sequestration credits. Countries with excess carbon capture, e.g., kelp farming, BECCS, reforestation, can sell credits to others. A carbon-negative industrial revolution. To develop industries that are carbon capturing, sequestering, renewable, and clean, we must fundamentally redesign manufacturing, energy, and resource extraction. Key steps. Prioritize bio-based and carbon sequestering materials, e.g., hempcrete, bamboo, biochar. Scale up renewable energy with integrated carbon capture, e.g., BECCS, biofuels, algae. Develop circular, zero-waste manufacturing systems that capture and store carbon. Decentralize industrial production through localized manufacturing hubs and microgrids. Establish carbon incentives, policies, and markets to reward industries that remove O2 from the air. By implementing these strategies, we can reverse industrial carbon emissions and build a truly regenerative global economy that heals the planet while providing for humanity. As the world faces the urgent challenge of climate change, industries must shift from being major contributors to carbon emissions to becoming solutions for carbon capture, sequestration, and clean energy production. This transformation requires a holistic approach that integrates renewable resources, circular economy principles, and emerging technologies to actively remove carbon dioxide, CO2, from the atmosphere while producing essential goods and energy. Below is a comprehensive framework for developing industries that are both carbon negative and environmentally regenerative. Carbon capture and sequestration technologies in industry. Carbon capturing industries must integrate advanced technologies that remove CO2 from the air and store it safely or use it in productive ways. These technologies can be applied to energy production, manufacturing, and resource extraction. Key carbon capture and storage, CCS, methods. Bioenergy with carbon capture and storage, BCCS. BECCS involves burning biomass, such as agricultural residues or wood waste, for energy. During this process, CO2 emissions are captured and either stored underground or converted into durable materials like biochar or carbon-infused concrete. This technology not only produces energy, but also actively removes carbon from the atmosphere. Direct air capture, DAC, with industrial utilization. Direct air capture, DAC, involves machines that extract CO2 directly from the atmosphere. The captured carbon can be injected underground for long-term storage or used to create synthetic fuels, plastics, and building materials. This approach ensures that CO2 is removed from the air while contributing to the production of sustainable goods. Biochar production for soil sequestration. Biochar is created by heating organic waste materials, such as crop residues, in a low-oxygen environment. This process locks carbon in a stable form, which can be mixed into soils to improve fertility and store carbon for centuries. This technique is highly effective in agricultural industries seeking to offset emissions. Algae-based carbon capture and biomaterials. Algae farms can absorb CO2 at a much faster rate than trees. The harvested algae can be used for biofuels, biodegradable plastics, and animal feed, creating a sustainable industry that simultaneously captures and utilizes carbon. Ocean-based carbon sequestration and kelp farming. Large-scale kelp farms absorb CO2 while restoring marine ecosystems. The harvested kelp can be processed into biofuels, fertilizers, and sustainable food products, ensuring that the carbon captured is stored in productive ways. Renewable and clean energy systems. A carbon-negative industrial sector must rely entirely on renewable energy sources while incorporating systems that capture and store carbon in the process. Carbon-negative energy technologies. Bioenergy and biomass power plants with carbon sequestration. Biomass power plants can generate electricity from organic waste, forestry residues, and algae. When combined with carbon capture technology, these power plants can remove more CO2 than they emit, making them a carbon-negative energy source. Green hydrogen from organic waste and biomass. Hydrogen fuel can be produced from agricultural and industrial waste rather than fossil fuels. When paired with carbon sequestration, green hydrogen becomes a viable alternative to gasoline and diesel while actively reducing atmospheric CO2 levels. Solar and wind energy expansion with integrated carbon capture. Solar and wind farms can be enhanced with carbon sequestering vegetation, such as grasslands, trees, and algae systems that further remove CO2 from the air while generating renewable power. Geothermal and tidal energy with carbon utilization. Geothermal power plants, which use heat from the Earth's crust, and tidal energy systems, which harness ocean movement, provide stable and renewable energy sources. CO2 capture from industrial processes can be injected into geothermal reservoirs to enhance energy extraction while storing carbon underground. Sustainable and carbon sequestering manufacturing. Manufacturing industries must transition from fossil fuel-dependent production to bio-based, carbon sequestering materials and methods that eliminate emissions while capturing CO2. Key sustainable materials and practices. Carbon sequestering concrete and bioplastics. Traditional cement production contributes to 8% of global CO2 emissions. However, new materials infused with captured CO2, such as carbon-negative concrete and algae-based bioplastics, can store carbon while replacing high-emission materials. Hemp, bamboo, and mycelium-based building materials. Hempcrete, a hemp-based alternative to concrete, bamboo, and fungal mycelium, can replace steel, concrete, and petroleum-based plastics in construction. These materials store carbon in their biomass while reducing reliance on resource-intensive industrial processes. Regenerative agroindustry for sustainable textiles and packaging. Fast-growing carbon-sequestering crops like hemp, seaweed, and algae can replace synthetic textiles and plastic packaging. Biodegradable alternatives prevent pollution while ensuring that carbon remains locked in organic materials rather than being released into the atmosphere. Zero-waste industrial models and circular economy. For industries to be truly sustainable, they must adopt zero-waste systems that upcycle all materials and eliminate emissions. Waste-to-carbon storage solutions. Industrial symbiosis, closed-loop manufacturing. In a circular economy, industries exchange waste materials, ensuring that one company's byproducts become another's raw materials. For example, CO2 captured from steel plants can be used to grow algae for biofuels, effectively turning waste into a resource. Biochar from organic waste for long-term carbon storage. Agricultural and forestry waste can be converted into biochar and stored in soil, removing CO2 from the carbon cycle while improving soil health. Algae-based waste treatment systems. Algae farms can be used to purify industrial wastewater while absorbing CO2. The resulting biomass can be converted into biofuels, replacing fossil energy sources. Decentralized and localized carbon capturing industries. Industries should be decentralized and localized to reduce transportation emissions and strengthen community resilience. Distributed manufacturing and energy production. Localized 3D printing and biodegradable materials. Industries can use 3D printing and local bio-based materials to manufacture products on demand, reducing waste and carbon emissions from global supply chains. Community-owned renewable energy grids. Towns and cities can establish microgrids powered by solar, wind, and bioenergy, ensuring localized and sustainable energy access while capturing carbon through integrated agricultural and forestry projects. Global scaling and policy incentives. To transition industries worldwide to carbon-negative models, governments, investors, and corporations must work together to incentivize clean and carbon-sequestering industries. Key economic and policy strategies. Carbon pricing and tax incentives for carbon sequestration. Industries that actively remove CO2 from the atmosphere should receive financial incentives, while those that emit carbon should pay taxes that fund carbon-negative initiatives. Public-private partnerships for carbon-neutral and negative technologies. Governments can fund research and development (R&D) programs for carbon sequestering technologies while incentivizing private companies to adopt these solutions. Global carbon markets for carbon sequestration credits. Countries and corporations can trade carbon sequestration credits, allowing industries that capture carbon to sell credits to polluting industries, creating a financial incentive for emissions reduction. A carbon-negative industrial future. By integrating carbon capture, renewable energy, circular manufacturing, and localized production, industries can transition from being major CO2 emitters to climate-positive systems that restore ecosystems and reverse climate change. These industries will not only sustain human civilization, but also regenerate the planet, ensuring a prosperous and sustainable future. A comprehensive plan for building a carbon-negative, renewable, and regenerative city. As climate change accelerates, cities must transition from being carbon-emitting centers to becoming carbon-negative, renewable, and regenerative hubs. A carbon-negative city must remove more carbon dioxide, CO2, from the atmosphere than it emits, relying entirely on renewable energy, sustainable infrastructure, circular economy principles, and advanced carbon capture technologies. Such a city would not only provide a high quality of life for its residents, but also help restore ecosystems and reverse climate damage. Below is a comprehensive framework for designing and building a city that is carbon-negative, self-sustaining, and environmentally restorative. Urban design for carbon sequestration and renewable energy. A city must be designed to integrate nature, technology, and sustainable architecture to maximize carbon sequestration and minimize energy consumption. Key features of carbon-negative urban design. Carbon sequestering buildings and materials. Skyscrapers and homes will be built using carbon-negative materials such as hempcrete, bamboo, algae bioplastics, and mycelium-based construction materials. Buildings will feature vertical gardens, green roofs, and algae-covered facades to absorb CO2 and improve air quality. Walkable, car-free, and public transport-centric layouts. The city will prioritize walking, cycling, and public transport over private vehicles. Roads will be replaced by green corridors with solar-powered electric trams, magnetic levitation (maglev) trains, and bike-sharing systems. Integrated urban forests and parks. Large areas will be dedicated to forests, urban farms, and green public spaces to enhance biodiversity and carbon absorption. Every neighborhood will have pocket forests and regenerative wetlands that store carbon and prevent flooding. Smart zoning for energy efficiency. Residential, commercial, and industrial areas will be strategically placed to reduce transportation needs. Buildings will be oriented for maximum solar efficiency, reducing the need for artificial lighting and heating. Renewable and carbon-negative energy systems. The city must generate 100% of its energy from renewable sources while simultaneously capturing and storing CO2. Key energy solutions. Bioenergy with carbon capture and storage, BCCS. Organic waste, forestry residues, and algae will be burned for energy, with carbon capture systems preventing emissions from entering the atmosphere. This process generates electricity while permanently storing CO2 underground or in biochar for agricultural use. Solar, wind, and geothermal microgrids. The city will rely on solar panels on rooftops and roads, wind turbines in urban and offshore locations, and geothermal plants for consistent renewable energy. Localized microgrids will distribute power efficiently, allowing buildings to share excess energy with one another. Hydrogen from organic waste and algae. Green hydrogen will be produced from agricultural waste and algae, creating a clean alternative to fossil fuels for transportation and industry. Algae-based carbon capture and biofuels. Large-scale algae farms will absorb CO2, while the harvested algae will be used for biofuels, plastics, and food products. These algae farms will be integrated into the city's water treatment facilities, rooftops, and lakes to optimize carbon capture. Sustainable and carbon sequestering industries. The city must only support industries that capture carbon, generate no waste, and operate on renewable energy. Key industrial strategies. Carbon sequestering construction and manufacturing. Concrete and steel production will be replaced with CO2-infused concrete, hempcrete, and bamboo structures that permanently store carbon. Factories will use biodegradable, plant-based plastics instead of petroleum-based plastics, circular economy, and zero-waste manufacturing. All products will be designed for reuse, repair, or composting to ensure that no waste is sent to landfills. Industrial parks will function in closed-loop systems, where waste from one process is a resource for another. 3D printing with carbon-negative materials. Localized 3D printing hubs will produce products on demand using bioplastics, hemp fibers, and recycled materials, reducing supply chain emissions. Biomaterials and regenerative agriculture in industry. Industries will produce hemp-based textiles, mushroom-based leather, and seaweed-based packaging, eliminating the need for polluting alternatives. Kelp and algae farms will supply raw materials for biofuels, fertilizers, and biodegradable plastics. Food production with regenerative agriculture. The city must grow its own food using carbon-negative farming techniques to eliminate emissions from industrial agriculture. Key agricultural strategies. Vertical and rooftop farms. Multi-story hydroponic and aquaponic farms will grow food inside buildings, reducing land use while absorbing CO2. Rooftop farms will provide fresh produce year-round, decreasing reliance on food imports. Regenerative soil farming with biochar. Traditional farms will use biochar, composting, and crop rotation to restore soil health and store carbon underground. Ocean-based food production. Kelp, algae, and shellfish farms will absorb CO2 while producing sustainable food sources. Zero waste and circular economy systems. A carbon-negative city must ensure that every waste stream is repurposed as a resource. Key waste management strategies. Composting and biochar production. Organic waste will be converted into fertilizer and biochar, returning carbon to the soil instead of the atmosphere. Waste-to-energy conversion. Any remaining waste will be processed in biogas plants, creating energy while reducing landfill emissions. Algae-based water purification. Wastewater treatment facilities will use algae to absorb pollutants and CO2, producing clean water and biomass for biofuels. Smart and decentralized infrastructure. The city will be equipped with artificial intelligence, AI, and blockchain systems to optimize sustainability. Key smart city features. AI-optimized energy and water systems. AI will monitor and distribute energy, water, and food resources efficiently, reducing waste. Decentralized microgrids and blockchain for carbon accounting. Blockchain technology will track carbon sequestration and emissions, ensuring transparency and accountability. Autonomous and electric public transport. Self-driving electric buses and maglev trains will replace cars, reducing transportation emissions. Government policies and global expansion. A carbon-negative city must be supported by strong policies and incentives to encourage sustainable development. Key policy frameworks. Carbon pricing and green incentives. Companies that capture carbon will receive tax breaks and financial rewards. Public-private partnerships for research and innovation. Governments will fund clean technology research, accelerating the transition to carbon-negative industries. Global replication of carbon-negative cities. Once successful, this model can be scaled globally to transform cities worldwide into carbon-sequestering ecosystems. A carbon-negative city is fully achievable with today's technology and innovative urban planning. By integrating renewable energy, carbon-sequestering industries, regenerative agriculture, zero-waste systems, and smart infrastructure, cities can become self-sustaining, climate-positive, and resilient against future challenges. Industries can employ a series of detailed processes to filter, capture, store, and ultimately convert pollutants and harmful gases into useful products. These processes generally involve 3 stages. 1. Capturing the pollutants at the source. 2. Storing or transporting the captured gases safely. And 3. Converting the captured gases into value-added products. Capturing pollutants at the source. Filtration and scrubbing technologies. Wet scrubbers. Wet scrubbers work by passing the industrial gas streams through a liquid solution, often water mixed with chemical additives, that absorbs or reacts with the pollutants. For instance, sulfur oxides, SO, and nitrogen oxides, NO, can be neutralized by reacting with an alkaline solution, like lime or sodium hydroxide, forming less harmful compounds that can later be removed or recycled. Dry scrubbers and adsorption systems. In dry scrubbing, solid sorbents such as activated carbon or specialized zeolites are used to adsorb pollutants from the gas stream. The gas molecules adhere to the surface of these materials, effectively removing them from the flow. These materials can sometimes be regenerated through heating or chemical treatment to release the captured pollutants for further processing. Catalytic converters. Catalytic converters use catalysts, typically precious metals like platinum, palladium, or rhodium, to accelerate chemical reactions that convert harmful gases into less harmful ones. For example, carbon monoxide CO is converted into carbon dioxide CO2, and O can be reduced to nitrogen N2 and oxygen O2. Chemical absorption for carbon dioxide CO2. Amine-based absorption. A common method for capturing CO2 involves passing flue gases through an absorber tower containing an amine-based solvent. Amines, which are organic compounds containing nitrogen, react chemically with CO2 to form a stable compound. The process is reversible, allowing for the solvent to be regenerated and the CO2 to be released in a concentrated form by applying heat, a step known as desorption. Physical absorption. Under certain conditions, typically high pressure and low temperature, physical solvents like chilled methanol can dissolve CO2. This method relies on physical solubility rather than a chemical reaction, and is often used in combination with other technologies for maximum efficiency. Storing and transporting captured gases. Once the pollutants, especially CO2, are captured, they must be stored or transported safely for utilization. Compression and liquid storage. The captured CO2 is often compressed into a supercritical fluid, a state where it exhibits properties of both a liquid and a gas. This supercritical CO2 can be stored in pressurized tanks or pipelines, making it easier to transport over long distances to a utilization facility or a geological storage site. Geological sequestration. In some cases, captured CO2 is injected deep underground into depleted oil and gas reservoirs or saline aquifers. Over time, the CO2 is trapped by geological formations, a process known as geological sequestration, ensuring that it does not return to the atmosphere. Converting captured gases into products, carbon capture and utilization (CCU). Conversion to synthetic fuels and chemicals. Catalytic hydrogenation. Captured CO2 can be reacted with hydrogen, ideally produced from renewable energy sources, in a process called catalytic hydrogenation. Using catalysts such as copper, zinc, or more advanced metal-organic frameworks, CO2 is converted into methanol or other synthetic hydrocarbons. For instance, the reaction CO2 plus 3H2 CH3OH plus H2O converts CO2 into methanol, which can then serve as a fuel or a chemical feedstock. Electrochemical reduction. In this process, CO2 is reduced electrochemically using electricity from renewable sources and catalysts. The reduction reaction can yield products like carbon monoxide, formic acid, or even longer-chain hydrocarbons, which have uses in fuel production and industrial chemicals. Incorporation into building materials. Carbon-infused concrete. A particularly innovative use of captured CO2 is in the production of concrete. Traditional concrete production is highly carbon-intensive. However, when CO2 is injected into concrete mixtures during curing, a process known as carbonation curing, it reacts with minerals in the cement to form stable carbonates. This not only sequesters the CO2 permanently, but can also enhance the concrete's strength and durability. CO2-based polymers and plastics. Captured CO2 can serve as a raw material for synthesizing polymers. Through processes such as copolymerization with epoxides, CO2 is converted into polycarbonates, plastics that are both durable and, in some cases, biodegradable. These CO2-based plastics can be used in packaging, construction, and consumer goods. Production of bio-based materials. Enhanced biomass production. Some processes utilize the captured CO2 to enhance the growth of algae or other biomass. For example, algae farms can absorb additional CO2, producing biomass that can then be converted into biofuels, nutritional supplements, or even used as a raw material in bioplastics. Integration into industrial byproducts. Captured CO2 can be used to create value-added byproducts such as carbon fibers or carbon nanotubes. These advanced materials have high strength-to-weight ratios and are increasingly used in automotive, aerospace, and construction industries. The process of filtering, capturing, storing, and converting pollutants from industrial emissions involves filtration and scrubbing, using wet and dry scrubbers, adsorption systems, and catalytic converters to remove harmful gases. Chemical absorption, employing amine-based and physical solvents to capture CO2. Storage and transport, compressing CO2 for storage or geological sequestration. Conversion, CCU, transforming captured gases into synthetic fuels, building materials, or advanced polymers through catalytic hydrogenation, electrochemical reduction, and carbonation processes. Biomass utilization, enhancing algae or biomass production to integrate captured CO2 into renewable bio-based products. These integrated processes create a circular economy where industrial pollutants are not simply emitted into the atmosphere, but are repurposed as raw materials for new, sustainable products, significantly reducing the overall carbon footprint and contributing to climate change mitigation. Converting captured carbon and pollutants into technologies. Once captured, the carbon and other pollutants are transformed into useful products through various conversion technologies. Catalytic conversion into fuels and chemicals. Catalytic hydrogenation. Captured CO2 can be combined with hydrogen, ideally produced from renewable energy, in a catalytic reactor to form methanol or synthetic hydrocarbons. For example, the reaction CO2 plus 3H2 to CH3OH plus H2O converts CO2 into methanol, which can be used as a fuel or chemical feedstock. Electrochemical reduction. In an electrochemical cell, CO2 is reduced using electricity and catalysts, such as copper-based catalysts, to produce a range of chemicals like formic acid, carbon monoxide, or even longer-chain hydrocarbons. These products serve as precursors for various industrial chemicals. Material synthesis and building materials. Carbon-infused concrete. Instead of releasing CO2 during cement production, captured CO2 can be injected into concrete mixtures during curing. The CO2 reacts with calcium hydroxide in the concrete to form stable calcium carbonates. This process not only sequesters CO2 permanently, but also often improves the strength and durability of the concrete. CO2-based polymers. Through copolymerization, captured CO2 can be reacted with epoxides to create polycarbonates, a class of plastics used for everything from packaging to automotive components. These polymers are not only durable, but can be designed to be biodegradable over time. Advanced carbon materials. Captured CO2 can also be converted into high-value materials such as carbon fibers or even carbon nanotubes. These materials have exceptional strength-to-weight ratios and are used in high-performance applications in aerospace, automotive, and construction industries. Enhancing biomass and bio-based technologies. Algae cultivation. CO2 captured from the air or industrial emissions can be fed into algae cultivation systems. Algae absorb CO2 rapidly during photosynthesis, growing into biomass that can be converted into biofuels, nutritional supplements, or even bioplastics. This process is both carbon negative and renewable. Biomass upgrading. Captured carbon can be used to enhance the growth of plant-based biomass in controlled environments. The biomass produced can then be processed into a variety of products, including bioenergy, biochemicals, and plant-based construction materials, integrating the processes into a circular economy. The key to transforming captured carbon and pollutants into technologies is integrating these processes into a circular economy. Closed-loop systems. Waste streams and industrial emissions are not seen as disposal problems, but as raw materials. For instance, CO2 captured from industrial exhaust is recycled into fuels, chemicals, or building materials, which are then used in further industrial processes. Digital monitoring and optimization. Advanced sensor networks and AI systems monitor emissions and the efficiency of capture and conversion processes. Data collected is used to optimize operations and ensure that the maximum amount of carbon is captured and converted efficiently. Economic incentives. Carbon credit markets and government incentives encourage industries to adopt these technologies. Financial models that reward carbon capture and utilization help make these processes economically viable at scale. By employing advanced filtration techniques, such as direct air capture and industrial scrubbing, combined with catalytic and electrochemical conversion processes, we can capture carbon and pollutants from the air and waste streams and transform them into valuable technologies. These methods not only reduce harmful emissions but also contribute to a circular economy where waste is continuously repurposed as a resource for fuels, chemicals, construction materials, and high-performance carbon products. This integrated approach is essential for mitigating climate change while driving innovation in sustainable industrial practices.